In this example, this is a wedge of mass capital M, and this small m is a particle which is kept at the top of this wedge, and there are no friction at any of the contact surfaces. The base angle as given is theta, and this particular height is h. Now what we need to find out is when this small particle it slips down and it reaches here, at that moment what is the velocity of the wedge. That is, please read the question before proceeding to see the solution and explanation of this particular question. Just observe. The moment this particle reaches here, the wedge won't be here. The wedge will be moving to the left, because in the horizontal direction, we can say in the horizontal direction, the system, which system? The system of capital M plus small m is free from forces. In the horizontal direction, there are no external forces. Free from forces from external source. So there is no external source of force in the horizontal direction. This implies the momentum in horizontal direction, remain conserved. Now, if the momentum remain conserved, the moment this particular particle reaches here, by the time it has already started moving, and it is already moving in the left direction. I am trying to show you the rough figure how it should look like. The moment this particular particle small m comes here, the capital M is already moving with the velocity v. Now what I am doing is, till the small m is in contact with this wedge slanting surface. So at that moment, let us say the small m is moving with a speed u. Now please note that the speed u is the velocity, u is the velocity of small particle, which is small m, with respect to the wedge. That is, it is not with ground reference frame, it is with respect to the wedge. Therefore, in ground reference frame, how does it look like? Just observe. We can resolve into two components. This is already u sine theta, and this is equal to u cos theta. What are these components? It is with respect to the wedge. But the wedge at that moment is itself moving in this direction with a velocity v. Therefore, in ground reference frame, this particle's net progress in this direction will be u cos theta minus v. Now, what is this? This is with respect to ground. It is with respect to ground. Now, as we are aware of that the system is free from external horizontal forces, and therefore the momentum remain conserved. If the momentum remain conserved, keep on observing. Also, we can say that velocity of center of mass is 0 in the horizontal direction. The center of mass does not move in ground reference frame in the horizontal direction. Therefore, we have capital M into V to the left side is small m into u cos theta minus V to the right side. Just rearrange the terms, and we have u is equal to capital M plus small m V divided by small m cos theta. Now, what we shall do is, we will think over the conservation of mechanical energy. Please refer to the figure and observe what are given. Here, the loss of gravitational potential energy of the particle when it reaches down will be shared as the kinetic energy of these two objects, capital M and small m. So, I am proceeding. Here, what we can see is that using conservation of mechanical energy, we can have mgh is equal to half mv square, that is for the wedge, and very carefully see half small m and the speed square. Now the particle is having two components of the speed. X component was there, you remember, u cos theta minus v, and the y means the vertical component was there, u sin theta. Therefore, it should be u cos theta minus v whole square, and u sine theta whole square. Let's try to simplify as far as possible this expression. So we have mgh is equal to half mv square plus half small m. Just observe u square cos square theta, u square sine square theta. So it becomes u square. Then in the expansion it will be v square minus 2uv cos theta. Then what we are going to do, we will be going to be putting the value of u that we obtained in the previous expression. So we further proceed. Mgh is equal to half capital M v square plus small m by 2, and now I am putting the values, and after putting the values we further proceed with, see, small u was how much, capital M plus small m, then it will becomes whole square v square divided by m square cos square theta plus v square minus 2u. U was again capital M plus small m into v divided by small m cos theta into v into cos theta. There will be many terms which will get cancelled, and finally we will be having, see, v square containing term can be taken common, and finally we have take 2 also that side. 2 times mgh is equal to v square. Also you can take m plus m common. So we have m cos square theta in the denominator, capital M plus small m, 1 minus cos square theta, which becomes sine square theta. And after rearranging the term, v square will be equal to 2 m square gh cos square theta after cross multiplying divided by m plus m, and within another bracket it is capital M plus small m sine square theta. This was v square. So v is equal to this. What is this expression? This is the expression for the speed of the wedge the moment the small particle reaches very near to the bottom of the wedge.